Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. Grothendieck told us that the study of affine algebraic geometry is equivalent to the study of commutative algebra. And what that means in particular is that geometric concepts in affine algebraic geometry should have an algebraic incarnation. So what I want to do in this video here is to show you what happens when we look at the geometric idea of going to an open set, localizing to an open set, and how we can interpret this algebraically. Okay, and so the notion is called localization in commutative algebra. Okay, so to motivate what goes on, I thought I'd draw a geometric picture. So we'll start with a very simple example. We're going to look at this affine space AN in coordinates x1 up to xn. And we're going to look at what's called a principal open subset. Okay, so what's a principal open subset? That means that you look at the closed set that comes from the zeros of a single non-zero polynomial function. Say this is f equals 0. We'll call that D, this f equals 0. And you look at the complement of that. So the complement of that we'll call U. So that's where everything away from this blue line curve there. Okay, so that's my principal open set. And since it's an open set, it's not directly an affine variety as we know it. Okay, so we have to be a little bit clever if we want to see how on earth it is going to be actually an affine variety. Okay, so let's see how we're going to go do that. And there's a little bit of a trick involved. Okay, and so the trick that's involved is the following. Okay, what we're going to do is we're going to add an extra variable y to the x1 up to xn. So now we're in affine n plus 1 dimensional space. Okay, and inside here I'm going to look at a closed subset, and the closed subset is defined by this single polynomial equation, y times f of x. Okay, so this x tilde is shorthand for the x1 up to xn. That equals 1. That's certainly a closed subset inside here, so it's an affine variety, and you can talk about its coordinate ring. This coordinate ring is, you just look at the polynomial ring in x1 up to xn and y, that's here, and you mod out by this equation here, which is y of f of x minus 1. So this at least is certainly something that is easy to understand, and we can look at in terms of affine algebraic geometry. And one way to think about this ring though is it's quite nice. You have the usual polynomial ring x1 up to xn, and you've adjoined a y, but y by this equation here is just the inverse of f. So you've just thrown in an inverse of f. Okay, so that's the first thing. Okay, so let's just have a little think and draw what this is here. Okay, so what does it look like here? So basically, if you look above where f equals 0, okay, if f equals 0 here, there's no way this can hold. There's no y value. That's the asymptote. So if you look at this purple sort of sheet, that's kind of like the asymptote for this. Okay, so no points of v lie over this f equals 0 locus here. But for each of the other points outside, so each of the points above u, there's a unique point. So that means this projection map here, where you just map x tilde y just to the x tilde, so you forget about the y coordinate, that projection map is actually a set isomorphism from this v to u. Okay, so at the moment, since this is an open set, you may think it's not a closed subset of this affine space, so it's not an affine algebraic variety. But the thing is that via this very simple and very natural map here, it is set-wise bijective with this v, which is an affine algebraic variety. So we can say, well, let's use the, let's make this pi that goes from v to u a isomorphism of affine algebraic varieties by making this induce the variety structure from v. Let that variety structure here induce the one on u. In other words, the coordinate ring of u is going to be the same as that on v. So that's going to be precisely what we have here, polynomials in x1 up to xn with the inverse of f adjoined. So just to be precise about what that means, you're looking at all these rational functions here, where g here is any polynomial in x's, and in the denominator you can have any power of f that you like. Okay, so that's rather nice. Okay, so the point of all this is here you have some affine algebraic variety, a very simple one, whose coordinate ring is x1 up to xn. That's how you think of it algebraically, as this polynomial ring. And to go to this open set u, which is the complement of f equals 0, you just invert f. That's the procedure of going to that open set. Okay, now, this is actually quite a natural sort of a thing to do, because another way to think about what are the regular functions on this u here is you look at all the rational functions here which are defined at every single point of u. And you can see, of course, that all of these rational points are defined at every point of u because, well, the numerator is just a polynomial, and in the denominator, the only zeros are on the complement of u. They're along here, right? That's the only place where that's 0. So you never have to divide by 0, so this is going to be well defined. And of course, they're the only rational functions for which you have that. Okay, so that's another way to see that this is a very, very natural thing to do. And it shows you how you can go to this open set. Okay, so that's enough of the motivation. And the basic idea is, and this is the sort of the principle, is that if you want to go local, you invert things. So we want to see how this works algebraically in general now. Okay, so what's a general algebraic setup? Okay, so we start with R is a commutative ring. Okay, so that's the first thing. And then we need something to tell us what can be in the denominator. And that's going to be sometimes called a denominator set. Okay, but in this case, I'm just going to call it a multiplicatively closed set, which is the more standard terminology for this. So I'm going to pick some subset u of R, and that's what I'll need as some data, and it's going to be called multiplicatively closed if firstly 1 is inside there, and also if you have any 2 elements inside this u, then the product is inside this u. So this is the usual closure operation that you expect. Okay, so let's just do some simple examples so that we can see what's going on here. So here you can take the ring R to be the polynomial ring in the variables x1 up to xn. I've written x tilde for short here. And the allowable denominators are picked to be 1, f, f squared, or the non-negative powers of f. Okay, so that's the situation that you want to look at here. Okay, let's look at a slightly different example. Okay, you have R is a commutative domain, and you look at U is going to be all the non-zero elements. So here you're going to divide by having the denominator any non-zero element. Something that's a little bit more interesting, R here is going to be the integers, and inside we're going to have U is just the odd numbers. So here we're going to allow odd numbers in the denominator. Okay, so let's see this procedure. So that's the data that you need to do this localization procedure, and let's see how it works. And we need one more thing. We need an actual R module. So it's fairly general. Okay, we can also work with more general R modules. So let's suppose you have this M. And the ones that are most important, of course, will be when the module is the ring itself. But this is also very important as well. And then we can look at the module of fractions, MU inverse. So at the moment, I just want to tell you what this set is. Okay, and as a set, it's going to be just a set of all fractions, M over U. M, little m in the numerator comes from the module, and the denominator comes from this U, which is inside the ring. Okay, and it's just some fixed multiplicatively closed set. And what is a fraction? I haven't defined what a fraction is, okay? So I need to define what a fraction is. So essentially, a fraction is an equivalence class of pairs, m comma u. And what is the equivalence class? So when the two of these fractions is the same, okay? M over u is equal to m prime over u prime, okay? So when does that happen to be the same? So I guess there are various ways that you can do this. So by the way, just to see that you do need the notion of a equivalence class, of course, if you multiply the numerator and the denominator by the same thing, say inside u, say by some u double prime, then you get the same fraction, right? You should get the same fraction. U double prime m should on u double prime u should equal this fraction here, okay? So we need some equivalence. And the easiest way that to do this is to just say that the cross products are equal. U prime m is equal to u m prime. That's what you might expect. Unfortunately, there's a little bit of a subtlety that's involved. So let me just write down what the guess is first. So u prime m is equal to u m prime. Or in other words, the difference is going to be equal to 0. Unfortunately, it's a little bit more subtle than that, okay? Because these may be the types of fractions that you're used to if you play around with just the usual fractions in terms of rational integers, okay? But unfortunately, you have to be a little bit more careful. So in general, you have to say that this is 0 after you multiply by some u double prime inside u for some u double prime inside u. Okay, so that's the situation that you have, is you need this little extra condition here. So it's a bit stronger than what you might expect. So just some words to say why this is true. So basically these u double primes, they're things that can appear in the denominator, so they're invertible. So multiplying by some invertible sort of element shouldn't change the fact of whether something is 0 or not. So if this is 0 in this sort of setting, even when you multiply by this unit, then this should kind of be 0, so this fraction should be the same. Okay, so this is just a definition for what a fraction is. Okay, so what is this equivalence relation that you have here? Okay, so if we go back to this example B here, hopefully you've seen this before. If R is a commutative domain and you let the U, multiplicatively closed subset, be all non-zero elements of this R, then this RU inverse is just the field of fractions. And one of the things that you know in this case here is actually you can add these, this is actually a field in this case. Okay, so you can add fractions together, you can multiply fractions together. Okay, so that's something that you have. And the same is actually true in this more general setting here. So let me just show you how that works. So firstly, suppose you have two of these fractions inside here. Can you add them together? So what would be the usual formula? So I guess you put them in a common denominator, and the easiest one is u prime. And then you just add, or to get this on a common denominator, you multiply top and bottom by u prime. So that's going to be the same fraction because of this condition here. So you get u prime m plus um prime. So this is the usual formula that you expect. And that's what you have here. So the other thing is that this is also a module, so you can multiply by things inside R. So it turns out that actually if you have a fraction like m on u prime, you can also multiply by a fraction r on u, which is inside ru inverse. Okay, so how does that work? Well, the formula you would expect is that you just multiply the numerators, rm. This is just module multiplication inside m. And then you just multiply the denominators. And that's the definition of a multiplication. Now these addition and scalar multiplication of fractions that I introduced are about as nice as you could possibly want. In particular, we have the following facts. So firstly, of course, the addition and the multiplication are actually well defined. Remember, these fractions are equivalence classes, so you actually have to check that something there to make sure it is well defined. So in particular, you have a addition from RU inverse back on this set here, and you can also multiply two elements of this together to get you something inside here, and that actually makes this a ring. Furthermore, for this MU inverse, you can multiply by things inside here, and that multiplication makes this MU inverse an RU inverse module. Okay, so this is really as nice a situation as you could want. Okay, so let's have a little look at an example. Example C again. Okay, so let's look at the ring structure that we have here. So this is ZU inverse, where U is the set of odd numbers. Okay, so that's going to be just a subring of Q. If you let U be all the non-zero numbers, you'll get Q, but if you just restrict it to this, you only get some of the fractions where the denominator is odd. So that's easy enough, and you can check, inside here, right? If you look at the fractions where the denominator is odd, okay, if you add in your two of these, okay, you'll stay such a fraction. If you multiply two of them, you get such a fraction as well. Okay, so let's do a little bit more of the general theory about what's going on to try to understand this procedure of inverting elements, localization in commutative algebra. So firstly, how is this ring related to the original? Well, there's actually a ring homomorphism, iota from R to RU inverse, and it's defined very simply. Okay, any element R inside here can get sent to R over 1. Okay, so remember we always allow 1 to be in a multiplicatively closed set, and part of the reason why we include that is so that we have this fraction here. Okay, so this is certainly a map, and it's actually a ring homomorphism, and that's quite easy to see. Okay, just from the definition of addition and multiplication. The other thing that comes out of, and this is the point of why we define this, is that the image of any element inside our multiplicatively closed set U here becomes invertible. Okay, and that's partly because you can put u's in the denominators. Okay, u gets sent to u on 1, and its inverse is 1 on u. Okay, it's as simple as that. In fact, it's the universal such object here. Okay, so if you know about universal properties, you'll know that what this means. So let me just briefly explain for those of you who have seen this sort of idea before. Suppose you have another ring homomorphism R to another commutative ring, such that all the elements inside U, when they map over to this other ring, become invertible. Then actually you have a map from this ring to that other ring that you have here. Okay, so that's what universal means. Okay, so we won't use that so much, but this is also tells you a reason why this is the correct definition. Okay, the construction mimics what you see with fractions with just ordinary integers. Okay, but actually the real reason why it's so important is because of this universal property. Okay, so let's compute some of these modules and you get a little bit of feel for the types of things that can happen. Okay, so let me look at a little bit of pathology, or something that you may think is pathology. And we'll go back to this little example here. We have the integers, that's the ring we start off with, and we localize by inverting odd numbers. Okay, and the module I want to have a look at here is Z mod 3. And I claim that if you pick a fraction inside here, m over u, that's equal to 0 on 1. And 0 on 1 is just a 0 in the module, so every element is going to be 0. So why is that? Okay, so to check the equality of fractions, what do? You cross multiply. So you have m and 0. So you have here 1 times m minus 0 times u. And you need to show that, not that this is 0, you need to show that this is 0 when you multiply by some element in the denominator. Now, of course, this is just equal to m, and if I multiply anything inside, so this is equal to m, and if I multiply anything inside this m by 3, you get 0. Okay, so that's equal to 0. So that tells you straight away that these two fractions are the same, so every element is actually 0. So the localization of m is equal to 0. Okay, so you may think that this is a bit of a weird result. Okay, if you're just used to just fractions, of course, this looks rather strange. But the way you should think about this, it's a natural sort of a thing, in fact. Okay, and the way you should think about this is that, well, odd numbers, the 3 inside this ring here, RU inverse, okay, is a unit. It's invertible. So 3 acts both as a unit on m, okay, because it's invertible, and it also acts as 0. So the only way it can act both as a unit and as 0 is if this localization here, this mu inverse, is 0. Okay, so one part of this proposition that I also forgot to mention, this second part here, is that, well, you have a ring map from R to RU inverse. So that means that RU inverse is an R module in particular. So you can take this tensor product. If you've seen this notion of tensor product, otherwise you can find this on one of my YouTube playlists. Okay, you can take the tensor product of these, and not only will this be an R module, in fact this will be an RU inverse module, and the RU inverse module is naturally equal to this localization here. Okay, so that's a rather nice different interpretation of this localization that you get. But of course, it requires you to do localization not for the module, but for the ring at least. Okay, so that's another nice interpretation. Okay, so this is one example, and I wanted to show you this first because now you can really see why you need this extra condition here and what type of effect that it has. Okay, so you may wonder that, oh, maybe when you do this localization, you don't get anything interesting, okay, because of that. So let's look at a situation where you will get something that's non-zero, and the module I'm going to pick is going to be the cyclic group Z mod 4. Remember, we're looking at Z modules, and we're going to localize them by inverting odd numbers, okay? So I claim that when you invert the odd numbers and you look at this localization, you still get Z mod 4. Okay, what does it mean by you still get Z mod 4? I guess that doesn't completely describe it. But remember, because you have this homomorphism here, okay, any RU inverse module is in particular an R module, so that Z module structure is Z mod 4. As an abelian group is Z mod 4. And it's also a module over the this ZU inverse. Okay, so all of these fractions, okay, it's a module over there. And it's quite easy to see how it's a module. I'll explain that in a moment. Okay, so let me just kind of explain to you why this ought to be true and how you should think about this sort of thing. And the key idea here is that unlike the other case, okay, where the odd numbers, okay, here there's an odd number which acts as 0, which also is invertible. All the odd numbers, when they act on this, that's already invertible because this 4 is a power of 2, okay? So let's make this precise. So remember, so if you're given anything that's a u, which is an odd number, so possibly in the denominator, right? Okay, it's an odd number. That means it's invertible modulo 4. So we can find an inverse modulo 4, say v. So that means uv equals 1 plus 4k. And let's look at this fraction m over u. Okay, so what is this m over u? Well, I can multiply top and bottom by something that's odd, and v has to be odd here, of course. So I multiply top and bottom by v. And I claim that this fraction here is just the same as Vm on 1. And why is this the same fraction as Vm on 1? I guess we have to do the cross product, products and check they're equal up to multiplying by some odd integer. Okay, so let's do the cross products here. So you've got on one side, you've got 1 times Vm. That's Vm. And well, you want to say it's the same as Vu times Vm. What can I do here? I can multiply this by 1 plus 4k. Because 4 acts as 0 on this. Okay, 4 acts as 0 on n. So this term goes, so you just get Vm, so that's the same, it's true. But 1 plus 4k is uv. So that's a Vu times. Okay, so that's this other product that you have here. So you see that indeed, okay, every fraction you can just write as something in the original module over 1. And that's going to be the set bijection that you have here, okay? If you want to know, okay, so you've got a map from, in fact, this map you can apply to any module, okay? You have that's also true for any module, okay? M maps to mu inverse. Maybe I'll write that in. So you've also got a map here for M to mu inverse. Okay, you've also got a map like that. And that will be an R module map, as it turns out. We can apply that here, okay? And that map has an inverse. So if you're given a fraction like this, how do you get the original thing here? So you just pass to this fraction here, and you just map it to this Vm here. Okay, and that also tells you how do fractions act? Okay, how do you divide by u? Okay, how do you divide by u? Essentially, you just multiply by multiplicative inverse of u. Okay, modulo 4. That's how that extra module structure works. Okay, so to get more complicated sort of examples and to understand the theory, we have this very, very useful proposition that I really want to tell you about. Okay, so so we've given you a relationship between R and RU inverse. Okay, so there's also a relationship between the categories from R modules to RU inverse modules. Okay, so there's a functor. Okay, from one to the other. So where does it send an R module? The R module gets sent to the localized MU inverse. That's an RU inverse module, we know. But to be a functor, it also has to take maps to maps, homomorphisms to homomorphisms. So suppose we have a homomorphism of R modules. What's the corresponding homomorphism on the RU inverse modules, MU inverse to NU inverse? So here, this is the set of fractions. So you just have to say where this fraction goes. And it goes to, well, you've got this map F, which sends the elements like M over to N, so you can apply that to the numerator. And divide by the same denominator. So basically, you just apply this homomorphism to the numerator. And that will give you what F does, what this functor, localization functor, as it's called, does on homomorphisms. And this will be a homomorphism of RU inverse modules. And that's quite easy to check as well. And what's nice about this is that this is actually an additive and an exact functor. Okay, so if you don't know what these terms are, I guess the most important thing to remember for now is that in particular, it will take direct sums to direct sums. Okay, that's one of the things that this will tell you. Okay, it takes direct sums to direct sums. And that will allow us to compute a lot more examples. Okay, so for example, if you want to work out what's the localization functor in this example do, okay, if you have any finitely generated abelian group, well, any finitely generated abelian group you can write as a direct sum of cyclic modules. So they all have this form here, m equals z over something. And I can write this in the form where I have that something on the denominator is an odd number, n, times some power of 2 to the a. Okay, so what's to work out the localization, mu inverse, of any finitely generated abelian group M, we just need to look at this case here. And in this case here, you can also write this as a direct sum of Z mod N, where N is odd, in which case you can apply this sort of argument to see that the result is 0. Or, and the other direct summand is going to be z on 2 to the a, in which case you can apply this sort of argument and you'll find that you just recover itself, okay, by the same sort of argument. So what you'll see in this particular example is that if you invert all the odd numbers, what will happen is that this cyclic module becomes what? The n will disappear and you get z mod 2a. So this is rather interesting, and it has some sort of actual number theoretic interpretation as what goes on, as you can see, okay? What happens when you localize this, okay? When you localize this, okay, you forget basically what's happening at odd primes. You just focus what happens at the prime 2. Okay, so that's why you only pick up this part here, z mod 2a. So this is the a very important proposition which allows you to calculate a lot of localizations of modules, and it tells you how the theory works. And this process of localization, of course, is very useful in algebraic geometry, but it's also very useful in number theory as well. I hope you enjoyed this adventure in pure mathematics.